Hello, welcome back. One more lecture, and today we do trees. We start with trees, we understand the terminologies of trees which are typically used, and then we also cover one of the types of trees, which is the binary tree, the most popular type, which is what we will cover in today's lecture. So where are we in terms of our syllabus completion? We are actually tracking a syllabus in terms of any generic university curriculum, and that if you see that a particular module which actually we are talking about, a module 3 syllabus for a particular university, actually has linked list and trees, and we have covered linked list at length in the last few lectures. Please feel free to visit those playlists. Today we start off with trees, and that's what we are doing. We are covering the basic terminologies of trees, and we will also talk about the types of the trees. And needless to say, the binary tree is what we will introduce, which is the most popular type of the tree. And after that, as usual, we will take the commonly asked questions in various forums, and then we will try to solve that also. So if I come back and start today's lecture on trees, then what we are trying to establish today is where are we in terms of the data structures that we had started off in this entire data structure curriculum. So we started off with this non-primitive data structure, and we had covered the linear data structure at length in all our previous sessions, right? And what we are doing today is basically the non-linear data structure, and typically in non-linear data structure we are trying to cover trees. So here is where we are right now, right? So what is a non-linear data structure? And till date we have covered linear data structures. So what is the difference between the linear data structure and non-linear data structure is what you already know, but I'm just trying to give you a bird's eye view of what it is. So if I take if I take two axes, let's take one axis as position and one axis as traversal, right? So if these are two axes against which we evaluate both linear and non-linear data structures, then a linear data structure, you know, is an array. Let us take this as an array. So in this array, so we can have elements like this, and these elements are actually stacked in the form of a line. So they are actually going from left to right. That means if we are here, we can only go forward. That means we can only go along a line, and this line is a line of contiguous memory that you already know. For an array, we have to store it in a contiguous memory location, and we access it. If we are at a particular address, we will go forward, then only we can access the next elements. So that's why we are saying that the positioning of the position in which the array is stored, or a linear data structure is stored, is in the form of a line, right? So that's how it is stored. Whereas if we talk about the tree, then we are talking about a hierarchical data structure. In this hierarchical data structure, we can have something like this. So we can have this looks like this. So this is what is a tree, right? So we have what? A hierarchical data structure. And in this hierarchical data structure, the positioning is based on a hierarchy, based on a relationship, and therefore the positioning has everything to do with how you go from one node to another. So if I am here in this particular node, then I should not be always going front. I can go here, I can go here, or I can go here, right? So I can go to any node for that matter. That is my children when I am at the top level node of that particular children block, right? So that's what the positioning from a hierarchical standpoint is concerned, or from a non-linear data structure. So position helps you to actually understand that how much or in what manner are you stored, and therefore in what sequence can you actually traverse, right? So positioning gives you the sequence in which you can traverse, and we talked about that sequence. It also gives you neighbors, right? So if I say neighbors, then for 5 there is one neighbor on the left and there is one neighbor on the right. But if you see, for this particular node, there is one neighbor here, one neighbor here, one neighbor here, right? So that's the difference between linear and hierarchical as far as neighbors is concerned, which position influences. And if you talk about the relationships, right, which also position influences, then the relationship here is typically 1 to 1, because from being here you can only go here, being here you can only go here, and so on and so forth. Whereas, as I said earlier, that being here I can go I can go from here to here to here to here. So I can go to any node, that is my children. So the relationship is also getting influenced by the position. How about traversal? If I take traversal, then my entire array, if I want to search for 9, then I have to traverse from left to right, and I am actually contributing to what? I am actually contributing to an order which is my time complexity, which will be an order of n, right? So that total size of the array is where I will have to put my time complexity as the worst case time complexity, where my traversal to find an element will actually be at the last, is assumed to be at the last, and hence will take order of n. However, even if we are going here, even if we are finding an element here, right? So even if we are traversing down the route to find this element, we have to go, this is 1, this is 2, this is 3, and this is 4. So we have to make 4 comparisons. So how many nodes is here? There are so many nodes here, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So out of 12 nodes, we need not have consumed. So my order of, it's not order of 12 then, right? So it's not order of 12 as compared to the linear array. So it has now become a sufficiently smaller number, because the order now is not order of n, but order of log n, or it could also be an order of n log n, depending on the way you are constructing the tree. And that's why you are actually finding your element in 4 iterations as compared to 12 iterations, because your node has 12 nodes. The worst case should have been 12 if it was structured in the form of an array. So that's the difference that we are trying to establish between array and a non-linear data structure, and how non-linear data structure actually becomes very efficient when it comes to searching and traversing. So if that is understandable, then let's move and quickly cover some of the terminologies. Root, very simple. If there is a tree like this, then my root is actually the element which has no parent. So here there is no parent, hence this is my root. And a tree will have exactly one root. You cannot have more than one parent in a tree. So that's what is a root. Second thing that we will understand is, what is a node? Anything that can store data is a node, which is inside a tree. So anything that can store some data will become a node. Even the root is also a node. So that's the definition and representation of a node. How about the next? In fact, for the next, let us establish a relationship. Now, if we are talking about a definition of edge. Now, what is an edge? An edge is, you take one node and you take one more node and you connect them. Then this becomes the edge, right? So the connection actually is the edge. And if this is the connection, let's count the number of nodes here. So we have one node here, 2, 3, 4, 5, 6, 7. So we have 7 nodes. So our n is 7. And how many edges do we have? Let us count that. We have 1, 2, 3, 4, 5, 6. So we have edges as 6. So can I say that my edge is equal to n minus 1? I cannot say that just by checking on one particular tree. If I take all possible trees, then always this will be something that can be said. So for now, because we cannot actually show all possible trees and then arrive at this particular formula, we will assume that this particular formula has been vetted, and therefore E is equal to n minus 1 is something that we can establish and use in our mathematical problem. So always remember, my edge will be one less than the total number of nodes, right? So that's on edge and nodes. Now, what is a parent? Definition wise, it's the same as what you know. So anybody who can traverse through a node, or sorry, any node who can traverse through an edge rather to reach another node, then that becomes the parent, right? So if I can actually go from B, if I actually can go from B and use a traversal, which is this edge, to reach a node from bottom to top, then that particular node that I have reached is my parent. So from B I have gone to A, that is from bottom to top. That is what I have done. So if from B I have gone to A, then that is something, wherever I have gone becomes my parent. From C I can use this edge to go up, and wherever I reach will become my parent. So a parent is basically a node which has one or more children. So that way also you can imagine that, okay, from A, if I can go down and reach my children, then A will become the parent. So that is also something that you can do. So this is more of a top to bottom kind of a scenario. So whichever way you want, you can interpret it, but it's a standard parent definition. And similarly, child will be a standard child definition, where we will say that okay, D, if D is a child, it means that which is basically directly connected to a particular parent. In this case, it is B, right? So if I actually take this again, I'm doing a bottoms up concept. I'm doing a bottoms up concept, and I'm saying that from particular node, if I can use an edge to go to another particular node, then I am a child. That is all I'm saying, right? So that is what is the definition of a child. From a node, use an edge to go up. If you can do that, then you are a child to that particular node, which is a parent. So this becomes the parent. So whichever way you want, define it, but as long as you are saying that I am using this edge to either go up or go down, and define parent and child interchangeably as you want. Now, if that is the case, then there has to be something where I don't have a node, I don't have a children, right? So some parent which doesn't have a children, G doesn't have a children, right? So G becomes a leaf node. So D also doesn't have a children, so E becomes a leaf node. F becomes a leaf node. The rest of all the nodes which do not have, or rather has a children, are not leaf nodes. And that brings me to the next definition, which is basically the internal nodes. So all those that were not the leaf nodes are actually your internal nodes. So D is a leaf node, so it is not an internal node. G is a leaf node, not an internal node. F is a leaf node, not an internal node. Why are they leaf nodes? Because they don't have a children. And everybody else are actually internal nodes because they have children, right? So all of this that I have marked in yellow all have children, and hence they qualify to become an internal node. What is a path? A path is basically from one point, if you want to go to some other point, right? Suppose you are here and you want to traverse here, right? So the path will be the edges that are connecting the source and the destination. So we can say that if I want to go from A to G, then what is my path? A to B to E to G. So I will be selecting this. So my path is confirmed as this. What is my path length? Count the number of edges. 1, 2, 3. So you have the path length of 3. So to go from A to G, you have to traverse a path whose length is 3. Suppose I have to go from A to F, then I have to go from A to C to F, right? So this is the path I will choose. Then what is my path length? Count the number of edges. A to C is 1 edge, C to F is 1 edge. So 2 is my number of edges, which means 2 is the length of that path. So that's on this particular path concept. What is my descendant? Take any node. Everybody below that node is the descendant. That includes your immediate children, children to children, children to children, and so on and so forth in a recursive manner. Take any node, take B. Everybody below B are the children. B has to be the ultimate super parent of everybody, right? Parent, grandparent, grand-grandparent, or whatever you want to call it. That means from B, whoever is your children, the children's children, all of that will become your descendant. So that's on the descendant concept. Similarly, if this is the descendant, then we will have something called as subtrees, which are similar to the descendant concept. So you take any node, and from that node, if you start, let's say, if I take any node for that matter, I will not take A. I was trying to take A. Let us try to take B. Any node, right? If I take B, then the subtree, which is basically a subset of the entire bigger tree, starts from B now instead of A. So I have changed the root. So I am saying A is no more the root, and B now becomes the root. B now becomes the root. So if B now becomes the root, then the tree from B will be all the descendants of B. D to E, E to G. This is what is a subtree. Why is it a subtree? Because this tree is already inside this tree. That is why it is a subtree. Right? Similarly, if I take, let's say, the same example, a subtree which is rooted at C. So if I take C as the new root, so I will say C is my new root. Then from C, who are my descendants? F. Right? So that then the entire thing now becomes a subtree because this is a part of this tree. So that's on the subtree. I hope you can understand what is a subtree. Please remember, take all the descendants from the node, you get a subtree. Sibling is the brothers and children. That is, they have the same parent. So D and E are actually siblings because they have the common parent in B. So it's a simple understanding here. Of course, if you don't have any child, there is no siblings. So there are no siblings under G, right? So G doesn't have any siblings, or rather G itself doesn't have any siblings because G doesn't have E as a parent. So I don't have any more child of E. So if there was one more child of E, then it would have been a sibling of G. So that's the example on sibling. Degree of a node is basically the outbound connections from that particular node. So if I take A, the outbound connections are actually these two edges, right? So in other words, I can say they are the children of a particular node. How many children does it have? So degree of a binary tree can be 0, 1 or 2 because they can have 0, 1 or 2 children, right? So every binary tree can have that. So in our case, let's say G has 0 degree, B has 2 degree. Then we can say that C has 1 degree, A has 2 degree. So what is the maximum degree I can go? 2. And this tree does have that maximum degree. Some tree may not have maximum degree. So it could, a tree could look like this, right? So then the maximum degree here is what? The maximum number of children that a particular node has. So A has what? 1. So 1 is the degree. B has what? 1. 1 is the degree. C has what? 0. So 0 is the degree. What is the maximum of this? 1. Right? So then this becomes the degree of the tree. Right? So the maximum degree of the nodes becomes the degree of the tree. As simple as that. So in this example that we were taking, this is how it was stacking up. Right? So then what is the maximum of this? If I take all the other nodes, I'll still see that A equal to 2 is the maximum. Or any other B equal to 2 is also the maximum. So more than 2 is not there. So then the degree of my tree will be equal to 2. So that's on the degree of the tree. So what does a leaf node's degree be? Leaf node's degree is 0 because degree represents the number of children. Leaf node doesn't have any children, right? So degree of a leaf node is 0. Degree of a tree, just now I have explained that for this particular tree, if I take all the degrees of the nodes, individual nodes, and take a max of the degree, I'll get the degree of the tree. In this case, degree of the tree will be 2. Right? So that's on the degree of the tree. Now, a very important concept is the depth. Now, the depth of a tree is what? Typically, what you will do is, suppose you are underneath water, right? You want to understand how much of depth you are underneath water. What do? You look up. Whatever is the distance you see from yourself to the surface is the depth of yourself. So, if I am at G and I look up, I am looking up, then my surface is here. Right? So I have to then see that how many edges do I actually need to go to actually go from G to the surface. The surface is A. So I have to go to the root. So from any node to root, how many edges do we actually traverse is what is the degree. So from G, I have to go to the root. So I will take 1 edge, 2 edge, 3 edge. So then from G, the depth of G, basically the depth of G is equal to 3. Why? Because from G, if I look up, I will see E, I will see B, and I will see A. So if I sum up the number of edges that I see, I will get 3. So that's the depth of a node. Right? So that's the depth of a node. So when we say that depth of any node, so if you see root node, right? If I take the root node, depth of the root. What is the depth of the root? So the root is A. Look up from A. You are already at the surface. You have to go to the root to root, no edge required, 0 edges. 0 edges means my depth of this will be 0, right? So the depth is always going from bottom to top. You have to look up and see how many edges you are actually going to traverse, right? So that's the depth of a tree. Now the next thing is the ulta of it, which is the height of a tree. Height means what? Suppose you are standing tall, you are looking down, that becomes the height. So you are here, then the height of A is looking down and going to the leaf node, which is having the highest path length, right? So we understand path length, like A to B to D is going to a leaf node. So D is a leaf node, yes. But A to B to E to G is also going to a leaf node, which is at G. Now the path length of this is the number of edges. Number of edges is 2. The path length of this is number of edges is 3, right? So which is the highest path length? This one, right? So then I will take my height as the height to be equal to the height of A to be equal to the one path with the maximum path length, which is 3. So height of A is 3. Height of B can go to D. D is the leaf, stop at leaf. B can go to E to G, stop at the leaf, don't stop at an intermediate internal node. Then what is the maximum? This path length is 1, this path length is 2. Therefore the height of B is equal to 1, right? And the height of a tree, if I take all the heights of A, B, C, E, F, G and take the maximum height, then the height of a tree is coming out to be height of A, which is 3. And invariably this will be the case, that height of the root will always be the height of the tree. Just think about it. If you are at the root, you will always be at the maximum height. So the height of the root will always be the height of the tree. You might want to see all the nodes and take a maximum height and ultimately get the height of the tree from the maximum height. So height of a tree, as far as a formula we can say, height of the tree is the max of the height of all nodes. Yes, that's a valid formula, but then there's no point in doing it, because height of a tree will be always the height of the root, because root will always be the maximum, right? So that's what is on the height of the tree. The last few things are on level. Level is similar to your depth. So if I say that I can draw a line here, line here, line here and line here. So this if I see the depth of a particular this particular line, this line actually constitutes of this node. Now what is the depth? Depth is, as I said, you look up and see how many edges you have to go to the surface. From A is already at the surface, so my depth is 0. Here my depth is 0. From B, if I look up, how many edges to go to the surface? Surface is at A, so 1 edge. From C also 1 edge, so my depth here is 1, right? So that is on the depth. Similarly here the depth will be 2, here the depth will be 3, right? So whatever is the depth is the level that you can actually say. So this is at L0, this is at L1, this is at L2 and this is at L3. Lot of books, lot of materials you will find where they have taken this first level as level 1 instead of level 0. You are perfectly free to do that. You can take it as L0 or L1, doesn't matter, but in your formulas, which you will see subsequently, be cautious on what you have taken as L0 or L1 and accordingly adjust the formulas. So all I'm trying to say is, while depth is when I'm at a particular position and I look up, then how many edges that I have to go to actually reach the top, that's my depth, right? But if I draw horizontal lines of each particular layer of that particular tree, then I will also get levels which incidentally will be equal to the depth. So the level will always be incidentally equal to the depth. Do not confuse level with height. Level is not the height, rather level is analogy can be drawn to the depth of the tree. That's what we have established here. The last part of the common terminologies is a null tree, and the null tree is actually a tree which doesn't have any node at all. That's what is a null tree. And a forest is any kind of subtree of a tree. So if I take A, B, D, E and G, and then I take C and F. Now pick up any node. Let's pick up any node. Let's pick up this node. If I pick up this node, and how do I create subtrees? I hope you remember. Pick up the node and all the descendants. So this becomes my subtree. So if this is a subtree, then if I just place this subtree separately, it will look like this. Starting from a different root, which is B, taking all the descendants, is a subtree. So if I start from C, right, which is a different root than A, and take all the descendants of C, I will get this. Now these are subtrees. That means these are chota mota trees, right? All these chota mota trees put together will create a forest, right? So this is basically all the forests. So I can also have a forest which starts from E and goes to G. E is a root, take the descendants, you get a tree, E to G. So the tree will look like this. So this is also part of the forest. It's a subtree. Is D a subtree? Of course D is a subtree, right? Any node is a subtree for that matter of a particular tree. So D is also a subtree and it is part of the forest, right? So that's on the common terminologies. So now let's move to the next main part of this particular lecture, which is taking the first common most popular type, which is the binary tree. Now if you see this example where we have a general tree like this, right? A general tree, the total number of children is something that is not restricted. So you can have 3 children here, you could also have 100 children here, right? But in a binary tree, you can only have 2 children at max. So you can have 0, you can have 1, or you can have 2. So these are the children that you can have in a binary tree. That's the first difference between a binary tree and a general tree, right? And what else that we can think about is that the positioning of B being the first element, C being the second element, and D be the third element is not relevant in a general tree. Whereas here B being 1 and C being 2 is very, very relevant in a binary tree. The left and right child have a significance in a binary tree, and hence this tree A to C and A to B is not the same. This is not the same in a binary tree parlance. So that's in a nutshell the qualifying criteria for a binary tree: 0, 1 or 2 nodes, not more than that. And the sequencing of the nodes, the left and the right node sequence, is very, very important. So that's on the binary tree concept. The second thing that we are talking about is the way in which a binary tree is depicted. So binary tree is a graphical structure, right? How do we represent a graphical structure then in our computer memory? So we will take the help of arrays. We can do it with linked list, double linked list, stacks. There are various ways to actually implement a binary tree in a data structure. We will take arrays for this discussion, right? So let us say that this is our tree, right? If this is our tree, and imagine how a human being reads a paper, right? What does he do? He'll go from left to right. Once he finishes this line, he'll go down, then again go from left to right. He'll go down, then again go from left to right, finish off this line, again go down, finish off this line. That's how he typically would read a piece of paper. The same way we will actually read this tree. So we'll go from left to right. We get A, we will position A here. Then we will go down. Then we will get B and C. We will write it here. Then we go down. We will get D, E, F. And that is something we will also write here. So that is how we will represent the nodes inside the element pockets of an array. And the array, we will do a 1-based indexing, which means the first will not be 0, but will be 1, 2, and so on and so forth, right? So that is something that we will attempt to do when we actually do a tree to array conversion, or tree stored as an array. Now what does this help us with? First of all, we have converted a graphical representation, or a non-hierarchical, or hierarchical representation, rather a non-linear data structure element, into a data structure where we have stored it in our memory, which is an array, right? Now, if we have done this, right, then how do we make sure that if we are storing something, if we have taken this particular tree and we have stored it here, then I should be able to also take this particular storage, which is the array, and reconstruct the tree whenever I want. So that is how every depiction or every mechanism to actually convert a physical object into a data structure needs to be. The physical object can be converted to a data structure. The data structures can again further be converted into a physical object. Now, if that is possible, then you are right. You have rightly done the data structure. In our case, if we have to convert this array back to the tree, then we need two things. Every relationship has to be something that has to come out of here. We have to know that B is the child of A. We have to know that C is the parent of F. We have to know that B has two children, D and E, right? So that we have to know from the array, right? How do we know that? It's very simple. You will take the parent rule, which is saying that if you are at I, whichever is the value of I, for example, we will take this example. If I is at 6, okay, let us say I is at 6. So who is this F? Then I want to know who is the parent of F. Then what will I do? I will say that I'll take a formula which is I by 2 and I'll take a mod of that. Not a mod, my bad. This is a floor. Yeah, this is a floor of that. So if I take I by 2 and we take a floor of it, what we will get? We'll get 3. So who is the parent? 3 is the parent. Let us see if 3 is the parent of F. So we are at F. Our F's parent is C, and at 3 we also have C. So that's right. So why are we taking this floor? Let us understand that logic, why we are taking this floor. Suppose we are at 5, right? If we are at 5, then I is equal to 5. What is the parent of this particular I equal to 5? It will be a floor of 5 by 2, right? So 5 by 2 is 2.5. So a floor value of that, which is equal to 2. So in 2 we will find the parent. So that means parent of E is going to be B. And that's why we take the floor, because 2.5 is a non-existent index and we cannot take the ceiling because that will be wrong, and therefore we take the floor of it. So that's on the parent selection. We also need to have, at any point in time, we should be able to tell what is our children, right? So how do we tell what is our children? Being somewhere, being in a particular parent, how do we say that you are my children, right? So the children formula is that if you are at, in fact, children has two formula. One is the left and one is the right. So being in a particular index, which is I, let's take I as 2, right? So I, if it is 2, then the formula says 2i. So 2i means 4. So being in a particular I, which is 2, that means who is the children of this parent B? 2i is the left child. That means D is the left child, because 2i is 4. So D is the left child of B. Yes, D is the left child of B. And who is the right child? The right child is, for I equal to 2, it will be 2i plus 1. That will be the right child, which is equal to 5. So for B, right child is 5, which is E. Yes, E is the right child. So that is how you will take a binary tree in the form of an array and reconstruct that array, or take that array and reconstruct it into the binary tree. So that's how you are flattening out a hierarchical data structure into a linear data structure, but still you are maintaining the hierarchy through these formulas that we have just now discussed. Right? Now let's try to figure out what are the various types of important types of binary trees that exist today. Now first thing is full binary tree. Full binary tree is also called as a strict binary tree. So every node will have 0 or 2. There is nothing called 1. So you cannot have a node which is like this. So A, B, then we have C, and then we have D. And here we have, let's say, E. You cannot have something like this. Why? Because this particular B has 1 children. This is missing, right? And this C also has 1 children. This is also missing, right? So you cannot have a tree like this and call it as a full binary tree. A full binary tree needs to have every node having 0 or 2 children. We had 1 children for B, 1 children for C, and hence this is not a valid tree, right? So that's what is the definition of a full binary tree. Next, if we take the next type of tree, we call it as a complete binary tree. In a complete binary tree, we are saying that all the levels are completely filled except the last level. So we can actually take any binary tree for that matter. Let us take a binary tree. So if I take this, and I start this, and I take this. Now this is not a complete binary tree. Why? Because if this is a level, 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 what can level 1, how many nodes can level 0 have? 1 node. How many nodes can level 2 have? Maximum 2 nodes. How many level nodes can level 3 have, or rather 2 have? 4 nodes. And this can have 8 nodes, right? So this particular area where L2 has 4 nodes, or is supposed to have 4 nodes, doesn't have 4 nodes. It has only 2 nodes. And that is why you have not filled all the levels. You have not filled all the levels except for the last level. Last level is allowed. For example, here, just check. Level 0, 1 node. Yes, okay. Level 1, 2 nodes. Yes, okay. Level 3 is supposed to have 4 nodes. You have 3 nodes. What went wrong? You are at the last level. So last level is allowed. Last level you can have 3 as compared to 4, which is perfectly fine. So that's a complete binary tree. Perfect binary tree is that where all internal nodes will have 2 children always. No 0 concept, no 1 concept, only 2 concept, right? So only you can have all the parents having 2 children, and all the levels will have all the leaves rather will be at the same level. So if you see the leaves here, these are the leaves. They are all at the same level, right? And that's what we are saying, that this is a perfect binary tree because all the leaf nodes are at the level of 2. So I cannot have something like this and say that this is a perfect binary tree. Yes, I can see that they have 2 children. All nodes have 2 children. All nodes have 2 children, and all leaves, of course we are not talking about leaves here, all internal nodes we are saying, right? All internal nodes will have 2 children. So this is a leaf, not an internal node. This is a leaf, not an internal node. This is a leaf, not an internal node. Rest, this node has 2 children, this node has 2 children. So that first point is satisfied. But all leaves at the same level. This is one leaf, this is one leaf, and this is the second leaf, third leaf. Are all of them at the same level? No. This is at level 1, and this is at level 2. So all the leaves are not at the same level. Therefore, this is violated. This is not a perfect binary tree. So that's how you will need to probably understand the definitions of a perfect binary tree. How about a skewed binary tree? The skewed binary tree says that every node has only one child, right? So it gets skewed to one side, right? You don't get a proper balanced kind of, or something, for lack of better words, a good looking kind of a tree. You don't get something like this, right? You get something like this, right? So this is the nodes. This is called a left skewed binary tree. And similarly, if it skews on the right side, then you get a right skewed binary tree. So what is the height of this binary tree? What is height? Remember the definition of height I told you? From the top, see the down. And the height of a tree is the height of the root. That's also something we had established. So what is the height of this particular tree? The height of the tree is the total number of edges. And we know that the total number of edges is equal to n minus 1. So the total number of edges for this particular binary tree, or any particular binary tree which is left skewed or right skewed, will be the height of the root. So the root height will be equal to what? Root height will be equal to the total number of edges, which is n minus 1, right? So it will be n minus 1. So if I have in this example A, B, C, D, how many nodes do I have? N is equal to 4 here. So the edges will be equal to 3. Why? Because edge equal to n minus 1, right? So this is 3. Therefore, my height of the root node is equal to 3. So what is 3? 3 is equal to n minus 1. Hence, the height of a skewed binary tree will always be n minus 1. right? If it is in the worst case skewed, that means it always goes right, 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 or left, 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 left. There is no deviation like this. It goes left, 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 and suddenly starts going right. I'm not talking about that. We are talking completely left skewed or completely right skewed binary tree. The height of that particular binary tree will be the total number of edges minus 1, as simple as that. And we have already established it earlier. So that's on the skewed binary tree. Then we also have a balanced binary tree, in which if we take the modulus of the height of the left and the right tree, then we are going to get something which is less than 1. So if I take let's say the left tree from the height of the left tree from A looks like this, and the right tree from A looks like this. So what is the height of the left tree? Height of the root is the height of the left tree. Height of the root is what? The total number of edges. So this gives me a height of 2. Height of this A gives me the height of the right subtree. So this is also 2, because the total number of edges is 2. So modulus of 2 minus 2 is equal to 0, and this is less than equal to 1. Then we have a balanced binary tree. So this definitely is a balanced binary tree. But if we have something like this, let us try to make an unbalanced binary tree. So if we have C and we have D, and then we have let's say E. Let me remove this. Yeah. Okay, so if we have this as a binary tree, then yes, this is a binary tree. Why? Because we have 0, 1 or 2 nodes, which is okay, right? Now what is the height of the left tree? Height of the left tree is 1, 2, 3. So 3 minus height of the right tree is 1. Modulus of this is 2. Is this less than equal to 1? No. Therefore, this is not a balanced binary tree. So in order to balance it, if you would have reduced this particular node and would have kept it somewhere above, then this becomes balanced. Why? Because the height of the left subtree now becomes 2, 1, 2, right? Height of the right subtree is 1. So this becomes, this becomes 1, and that 1 is, you are contributing towards being less than equal to 1, and hence the formula holds good, hence you are a balanced binary tree. So that is what is a balanced binary tree. A binary search tree is something which is very popular, and we will understand this in the next lecture on the binary search tree. But a binary search tree has the left subtree to have all elements which is less than the root, and the right subtree to have all elements which is greater than the root. Right? You take anything, you take the same thing and not just be focused on just that root. You take any node and observe the left and right. Right? So let us do that. 70, and then we have 60, and then we have 80. So let us observe that from the left subtree everything is less than 50. From the right subtree everything is greater than 50. Right? And if I take 30 as my root, then the left subtree is less than 30. My right subtree is greater than 30. If I take 70 as the root, then my left subtree is 60, which is less than 70. My right subtree is 80, which is greater than 70. Right? So that is how I will have to treat a binary search tree, where I know that at any point, any node I go left and its descendants will always be less than the root, and the right and its descendants will always be greater than the root. And that has a lot of significance when we try to sort a tree. We'll see that when we visit binary search trees. So now let's get into some mathematical concepts of how we actually discover certain things with respect to mathematics and the total number of nodes, total number of edges, total number of leaves. How do we put together all of that in order to calculate certain things? So the first concept that we'll pick up is, given a depth, can we say the maximum number of nodes that is possible at that depth? So for example, let's build the example. Maximum number of nodes of a binary tree, right? So if I have a node like this, then if I want maximum number, I cannot keep one node in level 1. I have to have 2 nodes here, because I want to consider maximum number of nodes. Similarly, at level 2, I have to have 4 nodes because we are talking maximum number of nodes, right? So I will not actually keep anything empty, right? So I hope you are understanding where I'm going. So we have, let's move one more level, or rather let us draw the levels so that you understand. So this is my level 0, this is my level 1, and this is my level 2. Can I say this is depth 0? Yes. Depth 1? Yes. Depth 2? Yes. Because my depth and nomenclature of levels are the same, because we are starting levels with 0 index. Now, if I am talking maximum number of nodes, then at L0 or D0, how many nodes can be there? 1. If I am talking L1 or D1, then how many nodes can be there? 2. If I am talking L2 or D2, how many nodes can be there? 4. All these are maximum number of nodes, right? So if I want to therefore try to find out a correlation of this one with the level number or the depth number, then I can say that 1 is nothing but 2 to the power 0, 2 is nothing but 2 to the power 1, and 4 is 2 to the power 2. So what are we seeing? We are seeing that if I go to a depth which is or a level which is at LK or a DK, then I will have something which will be 2 to the power K as the total number of possible nodes that is there, or maximum nodes that is there at the kth level. So maximum nodes at a given depth, whatever that depth is, that is K, will be 2 to the power K. So that should be your answer, right? So that's on this particular way to calculate or derive things. Now next is your maximum number of nodes in a binary tree of depth K. Now this talks about that whatever you discovered in the earlier instance was for that particular level, right? So we are saying that here in this level, what is my total number of nodes, or maximum number of nodes. Now the next question or the next maths that we are trying to solve is that given a depth, can we say that because we are at that depth, the entire binary tree will contain how many nodes, right? So let us take this example again. So we will take this maximum, right? So we are going to fill up all the nodes because we are talking maximum. So this is a depth, right? So depth, let us take depth of 0, let us take depth of 1, and let us take depth of 2. So these are all depth. Depth means what? Being at a particular node. Let's say I am here. If I look up how many edges I am going to go to reach my root, so I'll take one edge here and one edge here. That's my depth is 2 for this particular node. I just recap the depth concept so that you have a refresher there. Now the maximum number of nodes that we are actually seeing will be the summation of the total number of nodes for that particular depth. Now if I take depth 2 and I take this particular, or let's start with depth 0. Now in depth 0, what is the maximum number of elements that is possible? Depth 0, maximum number of elements possible is 1, right? In depth 1, what is the maximum number of elements possible in depth 1? Now this we had already established in the last example as being 2 to the power 0. In depth 1 we have 2, which we have established as 2 to the power 1. In depth 2 we have 4, which we are knowing that this is 2 to the power 2. Therefore at depth K we can say that it will be equal to 2 to the power K, right? So if I sum this up, so this becomes summation of 2 to the power I over I equal to 0 to K, right? And this becomes a geometric progression formula which becomes equal to 2 to the power K plus 1 minus 1, and hence this is your maximum number of nodes, because we took all the levels and in each level we calculated how many nodes. So we said, okay, you are at depth 2, you will have 4 nodes, you will have 2 nodes, you will have 1 nodes. Then we summed up all of this, that is my total number of nodes, right? And that formula came to 2 to the power K minus 1, sorry, 2 to the power K plus 1 minus 1, which is the maximum number of nodes of a binary tree of depth K. So that's on this particular topic. Next, let's calculate the minimum height of a binary tree with n nodes. right? So the minimum height of a binary tree. Now see, first understand the concept. If I take a binary tree and start building like this, is this minimum height? What is height? From the root, if I see down, what are the total number of edges? Height here is 3, right? But how many nodes do I have? 4. Now can I build a better tree where the height will be smaller with 4 nodes only? So can I take like this? This is 4 nodes, and this 4 nodes has created a height. So the height of this root is what? Number of edges to the longest leaf path, which is how much? Which is 2. So my height has reduced. Does my node change? No. The number of nodes still remain at 4, right? So we established what? That taking the same number of nodes, I can actually reduce the height of my tree by doing some optimizations like this. So I'm trying to make it as compact as possible, right? So that's what I'm trying to do here. Now if we take this kind of a tree which is compact, and this is actually the minimum tree given the size of n here is 4, then what can we draw in terms of the total number of nodes, or rather the height, the minimum height that we can actually achieve? Given 4 nodes, what is the height that I have to do? Now if you think about the total number of nodes, and just go back to our previous example. So we saw that given a level which is k, the total number of nodes is 2 to the power k plus 1 minus 1. That is the total number of nodes that are possible at a depth of k, right? So if I now take the height, then the height will also be the same, because if you see the height of this, or rather let's take this, the depth or the levels here is L0, L1, L2, right? So now if I say that the formula that we had earlier was 2 to the power k plus 1 minus 1 as the total number of nodes, right? So total number of nodes for a tree with level 2s is 2 to the power k plus 1 minus 1, where k is the total number of levels. So this is what we know. So k is the total number of levels, or the level number, right? So total number of levels here is L2. Now if we say that there are L2 levels, then the total number of nodes that are possible is 2 to the power of 2 plus 1 minus 1, which is equal to 2 to the power of 3 minus 1, which is equal to 8 minus 1, which is equal to 7. So total maximum number of nodes possible in L2, or in a situation where there are 2 levels, that is L0, L1, L2, because we are taking from a zero based indexing, is 7. And that is right, absolutely right, because if I take the 2 levels, then I can have 2 nodes here, 2 nodes here, 2 nodes here. So this is 4, this is 2, and this is 1. Total it up, you get 7, right? So we calculated it correctly. Now what are we trying to establish here? We are trying to say that if the total number of nodes is 2 to the power k plus 1, where k is the total number of levels, then we are actually saying that that is also the height of the tree. K can be also interpreted as the height of the tree. How? I'm not saying level is the height of the tree. I'm saying the value of that level, that is 2, is also the height of the tree. So what is the height of this tree? The height of the node, root node. So from the root node, if I go down to the longest leaf, how many edges am I taking? 2 edges, see? So can I say the height of this tree is 2? Yes, of course I can say. The height of this tree is 2. And the level of this tree, the max level of this tree is also 2. So I can substitute this k with the height also. So therefore, can I say that my therefore can I say that my 2 to the power h plus 1 minus 1 is the total number of nodes, when I say h is the height of the tree? So it has asked us to find the minimum height of the tree given n nodes, and I'm saying that given n nodes, the height will be something like this, right? So if the height is something like this, then that is my maximum height. Therefore, that is my maximum n, the total number, maximum number of n that we can produce. right? Now I have said that if we have to have the total number of height, so if we now figure this out, can this be ever greater than this? It cannot, right? Because this is the maximum. You can have less than this, so this can be less, but this cannot be more. So therefore, can I rewrite this by saying that n is less than equal to 2 to the power h plus 1 minus 1. Right? So for a tree with n nodes, we will have to have n is less than equal to 2 to the power h plus 1 minus 1. Right? So in that case, we can have the minimum height concept coming out of it. So if I actually say that if the number of nodes that we will generate out of, or the minimum number of nodes that we are going to generate, because we are taking minimum number of nodes, it has to be n is less than equal to 2h plus 1. So if n has to be less than 2 to the power h plus 1, again I will repeat why I am saying that 2 to the power h plus 1 minus 1 is the maximum number of nodes, and I want to see what is the minimum number of nodes, right? So I want to see the minimum height of the binary tree with n nodes, right? So I cannot say that I will cross n, right? So I need to say that I have to have this particular height that I have taken, right? It has to be always, so n max has to be greater than n, whatever is that value of n, whatever we are trying to find out, right? So n max has to be always greater than n. So what is n max? N max is 2 to the power h plus 1 minus 1. So it has to be greater than n, or greater than equal to n, and that's what we have written here. 2 to the power h plus 1 minus 1 has to be greater than n. So which means if we just shift the places, then 2 to the power h plus 1 has to be greater than equal to n plus 1. If we take log on both sides, then we have log of h plus 1, or rather log base 2, right? So we can just directly say h plus 1 is greater than equal to log base 2 of n plus 1. Therefore h is greater than equal to log base 2 of n plus 1 minus 1. Right? So that is your minimum height of the tree, given that you have been given n plus or n number of nodes. So that's how you find out the minimum height of the tree, right? So this is something that has come in one of the years in several universities questions. You can expect this kind of a question to come. So all you need to do is you need to derive it like this. Again, you will take the 2h minus 1, 2h plus 1 minus 1 is the n max, and n max has to be always greater than equal to n, right? So we are trying to find out not with the max nodes, we are trying to find out minimum height of the tree with n nodes. Why n will become suddenly less than n? Why n will become suddenly less than n max? Because this is or rather, let me take a different area. So this is the maximum nodes possible with 2 levels, right? Or with a height of 2. But can I say that my node could be this also? So what is this number of nodes here? 4. What is the number of nodes here? 7. But what is the height here? 2. What is the height here? 2. Right? So what am I trying to say? I'm trying to say that with the same height you can have lesser number of nodes also, right? The same height can actually be created with less number of nodes also, and therefore your n will be less than the maximum that is needed for substantiating this height. So n max here is 7. N max here is 7 for a height of 2. So therefore n can be any value, right, between certain numbers, and in this case n is here 4. N can be 5 also, n can be 6 also, n can be 7 also, but n cannot be more than n max, and that's why we have taken this line. This is our n max and this is our n, right? So that's how we are actually calculating it. I hope you have understood Let's move on to the next topic, which is maximum height of a binary tree with n nodes. Maximum height. How can I reach maximum height? Given n, I've been given 4 nodes. How can I get the maximum height? Put the 4 nodes back to back like this, or back to back like this. That is the only way by which you can get maximum heights. So your height is basically the n minus 1, because your edge will be the height, and we know edge is equal to n minus 1. So your h max will always be equal to n minus 1. Right? So all you are trying to do is, given n, you are trying to create a tree so that you maximize the height. So don't waste the nodes inside the same level. Do not create one more node here, because then you are not going to achieve a maximum height. Use that node to create one more height, one more height, one more edge, and go on. Then you create a skewed binary tree, and that's how you get the maximum height of a binary tree with n nodes. Now, if I take the relationship of a particular node with its leaf node, let us see what it comes to. So n0, let's imagine n0 has the number of leaf nodes. So what is the leaf nodes here? We have one leaf node as this, and one more leaf node as this, and one more leaf node as this. So our number of leaf nodes n0 is equal to 3, right? And the number of degree 2 nodes, that is our internal nodes, right? Internal nodes are degree 2 nodes. So the number of degree 2 nodes are 2. This is one degree 2 node. This is one more degree 2 node. Why degree 2? This is the 2 children. This is the 2 children, hence degree 2. All internal nodes will have a degree. So the n2, let's call this as n2, number of degree 2 nodes. In our case, the number of degree 2 nodes has become 4. Can I say n2 is equal to n0 minus 1? Yes, I can say that. Take any other example. Let us take this. Let us take this. Right? So let us take a simple example like this. What is n0? 2. What is n? n1? 1. So what is what is n2? Number of nodes with degree 2. So can I say n2 is equal to n0 minus 1? Of course I can say that. So this gets validated across any kind of tree that you want to take, which is the relationship between the leaf node and the degree 2 nodes. So that's the relationship that we have established. Now an interesting topic that I wanted to cover was the number of all possible binary trees with n nodes. Suppose I have given you 3 nodes. Let's take n equal to 3. Then you can draw a tree like this. Let's say I have given you, you can draw A, B, C. This is one way you can draw. So I have given you n equal to 3 nodes. You have put it like this. Can you draw a tree like this? Let's say C and B. You can draw that also as a particular tree which is different from this. We know that these two trees are not the same, because binary tree, left and right child, matters, right? In this way you can generate several combinations of trees. How many such combinations of trees can you generate given n? That comes with a Catalan number. No, this Catalan number formula is 2n plus n plus 1 n factorial. So given n equal to 4, the Catalan number, if you substitute, will be 14. So if I am giving you n equal to 4, that is 4 nodes, you can create 14 different types of trees. And similarly, if I give you n equal to 12, then you can create so many different types of trees. Right? So that's how we will have to interpret that, or we will have to understand that it's not humanly possible to do all the trees that we can do with various combinations using a particular methodology. Hence we will rely on a statistical methodology of Catalan numbers, and with Catalan numbers we can easily calculate the total number of possibilities of creating the total number of trees that are possible given a particular node size, given a size of n, right? So that's what is Catalan number used for. The next is on the minimum and maximum possible leaf nodes for n nodes. So what is leaf node? Let's say if I have n nodes, so if I have, let's say, 3 nodes, what is the minimum number of leaves that I can have? minimum means my leaf is the only leaf, right? So if I would have probably created it like this, then I would have got 2 leaves. That is not minimum. The minimum is this. So if I skew it on the left side, then given 3 nodes, my minimum is 1. And the maximum occurs in a perfect complete binary tree, which is n plus 1 by 2, the ceiling value of that. So maximum leaf will be let's say the ulta of this, right? So we can say that given 3, we can apply 3 plus 1 divided by 2 and take a ceiling of that, which is 2, as the total number of leaf nodes that I could create maximum from given 3 nodes. Let us redo this with some other example. Let us say that I have this as an example. So if I have this as an example, then maximum leaves here is how many? 1, 2, 3. So we have 3 leaves. And how many nodes do we have? We have 1, 2, 3, 4, 5 nodes. So apply the formula 5 plus 1 divided by 2 and take a ceiling of that. So you will get 3, which is the same as your total number of leaf nodes. So that way, what we are trying to say is that this is the only way, this is the only arrangement of the tree where I could generate the maximum number of leaves. 3 leaves, right? So with 5 nodes, I cannot generate more than 3 leaves. And the way I find it out is using this formula. I hope you can understand. Minimum is always going to be 1. Minimum number of leaves. Internal nodes versus total nodes. This is also interesting. We have already covered this, but let's do it. So if I say that this is, or rather let me draw it this way. So if I say that I have a node like this, right? So what is my internal nodes? My internal nodes are those which have children. So these are my internal nodes, and the rest are my external nodes, or rather I would say non-internal nodes, in the sense they are leaf nodes. So how many n0s we have? Leaf nodes 3. How many internal nodes we have? Ni's 2. So add them up. What do you get? Total number of nodes. So total number of nodes is equal to n0 plus ni. That's something which is very obvious, but that's something that we have established here. So moving on to the next topic, which is on the traversals of binary tree. Very important concept, very important topic. But before we get into the traversals, let's first understand what is the two major axis traversals that we typically do in a binary tree, or for that matter any tree. So one of them is called as the breadth first search, and one of them is, and the other is the depth first search. So as the words say, breadth first search, right? So if I draw a tree and I say that I'm going to do a breadth first search of this tree, that means I'm going to go from the breadth of the tree, that is from this direction. So this is how I will search the tree, right? Whereas compare it with the depth first search, which says that I'm going to go like this. This is the depth first search. So that's the difference between the breadth first search and depth first search. And in order to implement the depth first search, which we will shortly do, and we will understand the various kinds of traversals that we do in a depth first search, we will implement depth first search using a stack, right? But a breadth first search, if we have to do, we'll have to use a queue to do that. So that's typically how the difference between breadth first and depth first will go. But we will not worry about the nitty-gritties of breadth first and depth first search. We will try to deep dive into the various types of ways in which we can do breadth first search and depth first search. One of the ways which we are starting now is on the depth first search. What are the various mechanisms of searching a particular element in a binary tree? So typically what the three breadth first or depth first search concepts are: pre-order, in-order, and post-order. Now pre, in, and post are directly related to the concept of the root, right? So you have to remember that the logic in which the traversal happens is on the concept of the root. When I say pre, then the root is actually the prime axis. So root becomes pre. In every binary tree, you will have a root, you will have a left subtree, and you will also have a right subtree. or a right, you can say a subtree, or if there is no subtree, if it's a leaf, then it's a node. So we have the root, we have the left and the right subtree, and therefore if we are doing a pre-order traversal, then we'll say left root, we will say that root, left, and then right, because we are doing a pre-order traversal. Pre is from a concept of root, right? So the root has to be pre. So then do the root pre, and naturally the next is left and right, right? Because of natural sequence of left and right. So that's your pre-order traversal. In order to do a in-order traversal, in-order means is it in the right place? Is the root in the right place? Where do you think root needs to be? It needs to be in the middle, right? So that's why the in-order traversal will place the root in the middle, and on the left there will be a left, and on the right there will be a right, quite naturally. So that's the way in which we will do a in-order traversal. And for a post-order traversal, the post word means after everything. So the root will be at the post. So root will be here, then you will have a left here, and you will have a right here. So these are your 3 different types of DFS techniques, which we will now investigate in details. So let us take a standard tree, and we will use this same tree in order to explain both the pre-order, in order to explain all the 3, pre-order, in-order, and post-order traversals. So pre-order, we know by now, is take the root pre. Take the root pre means root has to be first, then left, then right. Now how do we traverse this? Right, so if I show you the traversal is easy. So we will go and we will visit the root, and then the visit will always be on the root, both for pre-order, in-order, and post-order. And what do we mean by visit? I'll come to that. Now the traversal request for the pre-order will be that, let's say if I start from here, then this is my root, right? So if I'm visiting the root, then I will print this A, that is the first letter of the tree that is getting printed in sequence. And I'll come to the printing part of it, don't worry about that. So when I actually print this, my next job is to go left. So my left subtree is this entire tree. So if we take the left subtree and then do the same thing, like B, D, and E represents my left subtree, and with this, if we do the same thing, that means we will take the root, which is B, and then go to the left subtree and then fire again a pre-order traversal on D, which will be again root, which is D, and the left will be nothing, right will be nothing, and in this way we will use recursion in order to cover the entire tree. So this basically means that we'll have to cover the entire tree at least once, right? So with that in mind, cover every node at least once, and that's what we call as visiting a node, right? So if we take the way in which we should be actually doing it, you can of course do it in various different ways, and the way I'm talking about is representing the stack that gets created using a recursion. That's the way I'm talking about. Then pre-order actually means these 3 things. Let me put it this way. Pre-order means step 1 is visit the root. The root is always the node that needs to be visited, right? So visit the root is the first step. So let me put it this way, visit the root. That is the first step. The second step is, once you are done, take the left subtree and do the same pre-order traversal. So call the same pre-order traversal on the left subtree, and next is do the same pre-order traversal on the right subtree. So that is what we want to do. We want to print the root always, and then we want to go to the left and go to the right, and when we go to the left, we will again do the same thing of printing the root, go to the left, go to the right, printing the root, go to the left, go to the right. That's how we will actually move the recursive stack. So let's see for this particular thing, how do we do it? So we will say that we will start a lifeline, which is basically the first step of that lifeline is to actually cover visiting the visit A. So this is going to be printing A in that sense, right? Visit A means you can do anything. You can print, you can search, any kind of operation. You are allowed to do that operation on this particular node. So visit A, and remember with this traversal, we'll have to visit all the nodes at least once. right? So we are visiting A, so A gets actually something that gets printed, so we will print A here, right? So let's say we are printing A. In terms of visit, we are printing A. You could be comparing things, you could be doing anything, we are printing just A. Now the next step that we have to do is the pre-order traversal of the left subtree of A. So which means that we have to say pre-order of B, right? So pre-order of B, because B is the root of the left subtree of A, right? So if we are doing pre-order of B, then the first step of this pre-order, as you are aware, is typically to do the visit of the root. So first step is visit root. So this, by the way, this entire thing is the pre-order of that particular root. So pre-order root, if we say, then this is how the algorithm looks like. So we have taken the first step here. Here we have taken the first step. This is the first step. This is the second step. The second step is going on, right? While the second step is going on, we initiated one more first step, right, of the next level, which is visit of the root. So what is the root here? The root is B. So visit B. So I will print B here, right? The next step of this visit, that this pre-order is basically create a lifeline to actually do a pre-order of the left subtree. The left subtree in this case is pre-order of D, right? So pre-order of D will initiate one more visit of the root. The root of D is D, right? So visit the root. The root in this case is D itself. Now after this visit of D, this will actually fire, which is going to say pre-order of a null, because D doesn't have any left. Then it will say pre-order of the null, which is basically the right subtree of D, which is not there, right? So that means that step 1, 2 and 3, this is step 1, 2 and 3 for D is over. So it comes back, it will come back, and step 1 and 2 of B was already done. So now it will do step 3 of B, which is pre-order of right of B. Right of B was E, right? So, and by the way, this should start from after this has returned. So the lifeline wise, if I just draw the line should start here, right? So that should be something that you need to be careful of. So we will do pre-order of E. Now pre-order of E means what? Visit E, then do a pre-order of X, because E doesn't have a valid child, and then do a pre-order of X again, because it doesn't have any valid child. So that means that we are done with 1, 2 and 3 for this also, and this completes the third part of this. So B is also, this particular child, this particular subtree is already done, right? So this particular subtree is done, and we were working with the complete A subtree. So pre-order B, that is the left subtree, is completely done, right? So now we are in a position to start our lifeline here with the right subtree. So the right subtree is pre-order of C, right? So pre-order of C means that I have done visit A, I have done the left subtree of B, I will do the right subtree of C, right? So the right subtree of C means what? That it will be visiting the root. So visit C, then it will say that it will go to pre-order of the left of C. Left of C is null, do nothing. Then it will say pre-order of the right of C, which is F. This pre-order initiates one more visit, that is another in order, right? Another pre-order rather of F, which is visit. So F now becomes the root. So visit F. Then it says the left of the root, which is nothing, and the right of the root, which is nothing, right? So the left and right of the root. So this way, this is also completed its 3 operations, and this returns back once this step done, then this also gets completed 1, 2 and 3, and we have already completed this 1, 2 and 3, right? So that way the visits, if I now notice, then I have to take those visits. Let us take those visits. I think we already started doing this. This is one visit we have taken, right, A. Then we will have to take the next visit, that is our B. So we will take B. Then we will have to take the next visit. So this is one more visit. Then we'll have to take this visit, which is our D. Then we'll have to take this visit, which is our E. What am I doing? I'm just going from left to right, top to bottom, trying to see what are my visits, right? So this is the next visit, which is C. And then we will take the next visit, which is F. And that is your pre-order traversal output of this particular tree. A, B, D, E, C, F. That is your pre-order traversal output of this particular C. Now, when you are doing this, remember that the output will always have the first element as the root of the tree. The first element will always be the root of the tree in a pre-order traversal. The traversal outcome will always be the root of the tree, right? So that's how you will do pre-order traversal. Next, if we move on to in order, the same way, let us do in order. In order is left root right, right? So left root right means we will say first, what is my algo? My algo says in order of left, then it says root. Root is always visit, I told you. Visit, root. Then we will say in order of right, right? So now you go here and just start with your in order. So you start with in order, and this entire thing is the algo for in order of the root, right? So this entire thing is the algo for the in order of the root. So we are saying in order of the root. Root is A. We start with this, right? So we have started with this. Our lifeline has started for this particular in order. Now with this in order, when you actually start this in order, then it actually calls the next level, which is our in order of the next particular sequence, which is in order of the left part of the in order, which is because we started with A, right? That is the starting point. So if we are now going inside, we will have to go inside and actually print the left side of the tree, because we are doing an in order of the left. So we will do an in order of B, right? So this is the next level of recursion that we have started. Now if we are doing in order of B, then we have to get inside that in order of B, because in order of B is not complete unless we reach a root, right, and complete the entire chain. So the in order of B will actually say that we have to also go inside and do one more lifeline for in order of D, right? So that is why we are saying that we will take the left, because all the in orders are going to happen over the left side of the story, and it's building this timeline. So in order of D will actually go inside this, and the in order of D doesn't have any left, so it will not execute anything. And when I say in order of D, then I have completed the left of D, so I will actually do an in order of a left of D, which is nothing. Then I will do an in order visit of the root. The root in this case is visit D. Then I will do an in order of the right of D, which is nothing, right? So this way I started to complete my step 1, 2 and 3. The next thing is this in order D is already done, because this has returned. This has returned means in order D is already done. So if in order D is done, that is the left part is done, you can visit the root, right? So then this lifeline starts to visit the root, not here, but after this lifeline ends. So we will start from here. So this will visit the root. In this case, our root is B, right? So because we started from here in order B, our root is B. So we will visit B, And once we visit B, we can actually go to the next statement, which is in order of the right. Right of B is E. So if I take the right of B, it is E, which is nothing but it will initiate one more in order of the left, which is null. Then a lifeline will start, which will visit E, which is the root, and then one more in order, which is the right of the root, that is E. So in this way, this also completes its 1, 2, 3, the algo, and this also completes its 1, 2, 3. Right now, if we actually now carry forward this lifeline, right, and we actually start from here, then in order B is complete because all of this has returned, right? So this in order B is complete. So if in order B is complete, then the next step is to visit B, right? So visit not visit B, sorry, visit A, because B is actually giving the next child or the next recursive stack. So we had started with A, so our root was always A, right? So in order B was the next subtree that we were actually taking it. So visit A. So visit A will take us where? Visit A will print A, or whatever we are doing at this point in time. And after that, we are free to do one more in order of the right side of the subtree. What is the right side of the subtree of A? The right side subtree of A is actually C and F, right? So we will say that the right side subtree is C. So to start with C, we will start with C here. Now when we start with C here, the starting point of the C part of it, then we will actually take that example where we are saying that we had taken in order of C. So now we are now going to go to the that is the right part of the chain that we are actually visiting, and therefore we will now need to consider this C as the next subtree. And in order to consider this C as the next subtree, we will say that okay, now go inside. The left part of this is nothing, right? So under C we don't have any left. So in order, we'll call another in order, right? So the recursive in order, and in that we have to do the left, because you see here we have to do the left, right? So the left of C, the subtree of C has nothing. Then you do a visit of C, which is your root, and then you do an in order of your F, right, which is your right subtree, and this completes this part of the story, which is 1, 2, and 3, right? And this completes your this part of the story, which is 1, 2, and 3, right? So if I now see what all we printed D from here, right? And then we printed actually there is one step that I missed. In order F is not going to be complete because in order F has to be executed. So this in order F will execute the in order of the left of F. In order of the left of F is in order X, which is not in existence. Then we will actually do a visit of F, and then we'll do a in order of a non-existent right, which is X. Then your 1, 2, 3 of the leaf node is complete, right? And once this is done, we are taking visit in sequence. So visit D is taken, visit B is taken, then we will take visit E, then we'll take visit A, then we'll take visit C, and then we'll take visit F. So the in order sequence will have wherever whichever pick up any node A, everything to the left of this in order sequence of A will be on the left subtree of A, and this on the right subtree of A. So that's the utility from the in order that we will get, that the left and the right subtree can be understood if you actually know any node, or you pick up any node as the root, then the left and right subtree of that particular node can be easily deciphered, right? So that's the beauty of the in order traversal. Now the last traversal is our post order traversal. So in this post order traversal, the algo will be like this. We will say that post order, and then by the way this is the entire. I'll go for post order of the root, right? So we will start with the post order of A. Now post order of the root means that you will do a post order of the left, a post order of the right, and a visit of the root. This is what we will do. So because our post order means the root has to be visited at the end. So if we actually start with the post order of A, right? So if we actually do a post order of A, which is our root, right? So we are starting here, then this will give rise to 3 steps, right? So what is the 3 steps? Post order of the left, so which will give rise to post order of the left of A, which is B, right? Now the post order of the left of B will give rise to the post order to the left of B. Post order to the left of B is the post order of D. Post order of D will give rise to the post order to the left of D, which is a non-existent node, and from there it can therefore start its next step, which is post order to the right of D. Post order to the right of D, which is also a non-existent node, and therefore the next thing that it will do is post order left is done, right is done, so it can do a visit of the root. So it will do a visit of D. D is my root, and then what will happen is this post order, it will continue its lifeline, and this post order D is done. So now the next step would be to go to the post order of the right of B. So we will do a post order, sorry, this line should be here to signify that they are at the same level, right? So we will do a post order of the right of B. The right of B is E, so we'll do a post order of E, and post order of E would typically mean the same way as the top. There is a no left to that E, so post order of X. There will be no right to that E, so post order of X, and then we will do a visit of the E, which is the root of us, right? So that completes this. Now I can print the root also here, so visit B, which is printing the root, right? Now this B therefore now can do, this was the left subtree, so now it can go to the right subtree. So the right subtree of this would be my post order of C. So the post order of C will have the post order of F, and the post order of F will have the post order of the left subtree of F. In fact, my bad, because we are going right. So when we do the post order of C, then we should take the left. So post order of C's left is nothing, right? And then we take the post order of C's right. C's right is F. So that initiates one more recursion, which is post order of the left of F, which is nothing, post order of the right of F, which is nothing, and then the visit of the root, which is F. And once this is done, I can visit the root, which is C. And once this is done, I can visit the root, which is A. And that's all. So here we have the steps of 1, 2, 3, 1, 2, 3, and then 1, 2, 3, 1, 2, 3. Everywhere we have completed all the 3 steps of recursion. And then what we have also done is that we now need to print all the visits, which is D, E, B, F, C and A. And if you notice, the last element is the root. So from the pre-order, the first element is the root. From the post-order, the last element is the root. And from the in-order, any element you take, left side elements will be the left subtree of that element, right side elements will be the right subtree of that elements. So we'll utilize that concept to do two things. First, we will try to build a tree given a postfix expression. So given a postfix expression, and postfix is an expression which is very friendly to a computer because it can easily use a Q to evaluate the postfix expression, right? So check my video on Q, you'll understand why I'm saying that. Now, if I take a Q and try to solve this problem and also construct the tree, right? So what we will get is all the operators we will start pushing to a Q, right? So let us start to push things into a Q. I'll take a large Q because the expression can be a bit big. So first layer I will be pushing A, right? So this is done. Next I will push B. Next I will push C. All the operands will be pushed to the stack, right? So all the operands will be pushed to the stack, and I'm not sure if I said Q a few minutes back. We are going to evaluate it using a stack. If I have, my apologies for that. So C is also done, and now we are going into a star. Star is an operator. So write star here, and we will pop the element which is C and put it to the right of this star, right? And we will take B and put it to the left of this star. This is very important. The first pop will go to the right of the star, which is the operator, and the next pop will go to the left of the star. Aggregate this as one single number, because B you don't know, C you don't know. If you would have known, B star C would have been performed here. So what would you have got? One single number. So to represent one single number, I am taking the brackets. So I will say therefore that this B star C I will now push back into the stack. So now if I push back into the stack, I will get something like this, B star C. So this job is done. Now immediately what I will do is, when I am building an expression like this, I will also create the tree as we go along. So I got B star C. Doesn't it mean that I would be looking at something like this, right? This is our B star C. Star is the root, and B and C are the left infix, left and right operands of the star, which is our operator, right? So that's how we are building the tree as we go along the way. Now once that is done, we get plus. So put plus here, and let's pop out the first element, which is B star C, write it to the right, and then pop out the next element, which is A, write it to the left, and then take the entire thing and push back into the stack. So you get A plus B star C. Don't forget the brackets, because now this is a composite number and not the individual variables, as I explained earlier. Now what you will do is that this entire expression, what does it mean? You already have B star C. So start building the tree. So B star C is one operator to the, or rather operand to the right of this operator plus, right? So to the right of this operator plus, we have an operand which is B star C. So B star C is this right operand. So then there must be an operator at the top, which is our plus, which will eventually have a left operator as A, left operand as A. So what we have done is, we are saying that this entire B plus C, which was a number, is this, right? So this is one single unit. So one single unit with the plus and A should be composite tree. So one single unit with the plus and the A. So the plus will be in between A and that single unit B star C. So plus is in between A and B star C, right? So this way we are building the tree. The next step is for us to take D. So we will take D, we will push it into the stack. Next step for us is to take E, push it into the stack. Next step for us is to take star, and then when we get star, we will pop out E, put it on the right, pop out D, put it on the left. The right left do not mix. Take this as one single variable and push back into the stack. So D star E. So D star E, if you push into the stack, then first things first is we do not know what is the relationship of D star E with this particular tree. So we will just keep it alone for the time being. So this is D star E. Right? Now next is our F. So F will be pushed back into the, or pushed into the stack. Then we have plus. So plus comes here, and then with plus I will pop out F, which will go to the right, and I'll pop out D star E, which will go to the left, and entire thing I will put in bracket and I will push it back to my stack, which is D star E plus F. Right, so we will do that. So this job is done. So we will now integrate this D star E with a plus and take the F on the right. Right, so that's how this will look like. And the rest of this is, so plus is done. So now we have G. So G will go here. And once G goes here, we have star. So star comes here. And in star, what do we have to do? We have to pop out the stack, which is G. And the left of the next pop will actually take the left operand, which is our D star E plus F. Right, and this entire thing now becomes one single number. So this one single number is something that we will now push into the stack. Right, so let me just create some space here and push that thing into the stack. So we will be pushing 3 brackets, don't forget that, D star E plus F star G. We have pushed it into the stack, so we have to take this star G root. So star G means that this is my star G. Right, so that takes care of my subtree building. Now the next step is my star is done, so I have to just say plus. So I have got plus, so I'll keep plus here. I will pop this out, take it to the right. So 3 brackets, D plus E, this was D star E, and then we have a plus F. Let me write this neatly. So we have a plus F and then star G. We have a star G. Right, so that is the right side, and the left side is, my left side is A plus B star C. So as you can see, this particular thing is my right operand, right, and this particular thing is my left operand. So we need to integrate them using a this operator, which is plus, this plus operator here. So we will do a plus operator here, and then we will integrate these two. That creates my tree. So this is my whole tree. Right, so this is how we will actually convert a given postfix expression. So if it is postfix only, you can do it in this manner, because postfix can be easily solved from the stack. So the solvability of postfix is much higher, and we will do it in this manner. So this is this, and if you want, let me see this part of it. If we can select it, then we can bring it down and make it a bit neater. You will anyway have your examinations copy. You might be doing it with pencil, so then it will be a bit neater, and you can actually show a relationship like this, because this is at the same level. this is at the same level, right? So we have to make this at the same level if you have to draw it in a proper manner. But it doesn't matter that you can actually have the levels of the left and the right subtree not match. Nobody is forcing you to do that, right? So that's how you will take an expression, get into the stack, and then use the stack to create the infix expression of it, and then we are building the tree as we go along the way. So what is this called? This is called an expression tree. So sometimes you might be asked to build an expression tree, and this is your expression tree, right? So that's on the expression side of it. If we just take the mechanisms of post order and inorder that we understood we said that post order, the root is always at the right, and inorder, whatever node we pick, left side is all the elements will represent the left side subtree, and the right side will represent the right side subtree. With that funda, let us construct a binary tree. They have given the post order and inorder, so they will give you typically post order inorder and ask you to construct the tree, or they can give you pre-order inorder and ask you to construct the tree. But giving you inorder and rather post order and pre-order and constructing the tree, that's impossible to do. So that's not something that you can expect. So just understand that post order inorder or pre-order inorder combination will be there. Now if I just see here my post order, the first thing that I will take help from post order is this, that A is the root of the tree. So if A is the root of the tree, then I will go to inorder and say, inorder, A is the root, please tell me what is the left subtree and the right subtree. So the inorder will happily tell me that the left subtree is this and the right subtree is this, right? So what we will do, we will start drawing the tree. So we will say that we will start drawing the tree in the sense that we will say A is my root, which we have identified. The left and right, there will be something we do not know, but we at least know that D, B, G, E, these will be to the left of A, and C, H, F, I will be to the right of A. This at least we know. Then we will go to the post order and say that if this is my subtree, so a subtree is also a tree, right? So if this is a subtree, then this will be my what? This will be my root, right? So if this is my subtree, actually this. So we will say that once we have identified DBGE to the left subtree, all we need to do is we will try to understand if this was the left subtree, then what is the last element in the post order sequence, right? So we will see what is the last element in this post order sequence from DBGE. So if you go from the right to the left and try to evaluate this particular expression and see which of these alphabets come from the right to the left, right? What comes from the right to the left first? Does D come first? D comes here, so obviously that's not the first. B is here, right? What is G? Where is G? G is further, so B is still the winner, and then E is before B, so B is the winner. B is coming first when I see from right to left, so therefore B is definitely the root, because we are talking post order. B is definitely the root of this particular left subtree. So I can therefore write B here, right? So B is definitely the root. Now I can go to inorder and say that I have found that B is the root, right? I have found B is the root. Give me the left and the right. So they will, inorder will say, okay, I'm happy to give you the left and the right. The left of B is D and the right is GE. So the left of B I know. So now I know left of B is D and the right is GE. So right I still don't know, but I know G and E will be there. G and E will be there. So the same thing we will do again. We will take G and E and start searching in this particular pre-order sequence from right to left. Which comes first? Does G come first or E come first? Of course E comes first. Therefore E is the root of this chota mota subtree. So E is the root, which means that E becomes here, and with E, so E is the root, so we will take E from here and we will go to the inorder, and we will ask inorder that give me that if E is my root, give me the left and the right subtree. That there is no reason for that because we know that only G will be the left subtree, because it was already established that the right subtree here had G and E. So we will definitely say that E is my root, but then I do not know where do I place G. I know there will be only G, but I don't know whether I should place it to the left or the right. So if I see E and I tell that if E is the root, then what is the left subtree? Then it will tell me G is on the left. So I will now happily place G towards the left. So that part is also done. So the left subtree is completely done. Now we will focus on CHFI, which is my right subtree. So CHFI, same funda, we will go from right to left on the post order, right? So we will go from right to left on the post order, and we will try to figure out which of the alphabets come first. I can definitely see C comes first. I don't need to check for anything else. So I will say take C from here, right? And I know that C has become my root, so I will take C as the root, right? And I do not know what is the left and right of C, so I will go and take help of inorder. So I will say inorder, I have C, tell me what is the left and right, right? So inorder will say, okay, you have C, so your left and right would be E, because DBG is already part of the left subtree, and HFI on the right. So you definitely come to know immediately that you have E on the left subtree, and you do not know what is on the right node, but you definitely know that H, F and I will be part of your right subtree. So H, F and I you take again and move to the post order from right to left. Which comes first? I can see C coming, F coming first, right? So I can see F coming first. So with that F, right, I will go and therefore I know that F is the root. I will print the root here, and then I will say that I'll go to inorder and ask it that tell me the left and right of F, right? So it will tell me that you have found F, excellent. So the left of F is this, which is H, and the right is I. So immediately I know, therefore F left is H and F right is I, and that completes my binary tree construction given a post order and inorder traversal. So very simple. Post order means search for the root, and then for subsequent things search for the alphabet from right to left first time it occurs, and inorder means take help for the left and right subtree construction. So that's on this particular problem. A similar problem we will take, let's say, and we will try to solve it on the on a different perspective, which is given inorder and pre-order. So I told you, right? So they will give you inorder post order or inorder pre-order. So given the inorder and pre-order, we will now start constructing the tree. Same funda. First, pre-order means that we know that my root is to the left, right? So don't forget we are now at pre-order, so we will do it to the left. So A definitely is my root, which is what we know, right? Now we will go to inorder and say I know A, please tell me what is the left subtree of A and right subtree of A. So right subtree we immediately get what is my singular node, which is C. I don't need to actually worry about the right subtree anymore. So this is also done. And the left subtree, it says that I do not know, but I know that the subtree will look like this, DBFEGH. So with this DBFEGH, I will now start searching the pre-order from left to right, right? So if I search it, what is the first thing that I see? The first thing I see is B from this particular list, right? So that is the first thing I see. So if I see first that, then B definitely becomes my root. And if I take B and ask inorder that what is the left and right of B, so it will say left is D, left is D. Right, I don't know. I can tell you FEGH is to the right. So it will say that I don't know, but I can tell you this much, FEGH is to the right. So with this FEGH, we will then start searching in this direction, right? Which comes first? FEGH, I can see E coming first. So I will put E as the root, right? And then I will say in order, tell me, so E is done. So in order, tell me, given E, what is the left and right? So in order, we'll say given E, left is F, right? So I will put F. I will put F here, left is F, and G and H will be right. So G and H is right, but I don't know what is G and H. So I will go to pre-order again and I will search out of GH which comes first. So I can see G comes first. So immediately that becomes my root, right? Immediately that becomes my root. Now I'm left over with H. I know H will come as a root to the G, but I don't know where it will go. So I will again take help of this particular in order. Now say that G I have found. Please tell me the left and right root. So it will say H is the right. So I will say H is the right. Now if you see carefully, then you will see that this particular here we had said that B, the right part of B, we said will contain FEGH. See, the right part of B contains FEGH, right? So that's how we are actually validating ourselves and saying that we are constructing the question properly. DBFEGH is the left part of A is what we had said. So DBFEGH is the left part of A. So this is how we will typically do these kind of problems. Very easy, but be concentrated and try to attempt it with full concentration. I'm sure you will get this correct. So that's pretty much what I wanted to cover. Let's see what kind of questions typically come. We have proved that the binary number of nodes, maximum number of nodes of a binary tree of depth k is 2k minus 1. Now here we had covered it. We had said that the maximum number of nodes n max is equal to 2 to the power k plus 1 minus 1. You can go back in the lecture and see, and we had assumed that our first level is level 0, right? So with this this will come, but here it talks about 2 to the power k minus 1, which means that this k plus 1 has become k minus 1. So that means that this is considering the L0 to be L1, and that's why that difference of 1 is coming. So as I said, you are free to choose L0 or L1, and depending on what has been asked, you will have to intelligently figure out whether you need to select it as L0 or L1. So if I just do an L1 selection, then at an L1 layer, let me just use this particular space. So at an L1 layer, I can have maximum 1 node. So this is basically equal to 2 to the power of 1 minus 1, right? Because this 1 is from this 1, and then I give a minus 1 on forcibly to get to the power 0, which is equal to 1. So that is my 1 node. At the L2 layer, I can get 2 nodes, right? So which is basically equal to 2 to the power 2 minus 1, which is 2 to the power 1, which is equal to 2. And at the L3 node, I will get 4 nodes, which is equal to 2 to the power 3 minus 1. So which is 2 to the power 3 minus 1 would stand for 2 to the power 2, and that would become 2 to the power 2 means 4, right? So that's how we are actually getting this storyline. So at L equal to k, we will get the total number of nodes at 2 to the power of k minus 1, right? So that's how we will, or that's why we can say that the total number of nodes is 2 to the power k minus 1, basis the choice of L0 becoming L1. This is how the question was framed. So the next question is the number of all possible binary trees with 4 nodes is, and this is from the Catalan number. I don't know whether it is correct or not. I think we did it. So let's go back and check. A 4 node and a 12 node Catalan number sum we had already done, right? So that is here. Where is that Catalan number? Max and 2. Yeah. So 4 nodes is 14 and 12 nodes is a large number. So let us see if we have those options. there were 2 sums that came in the similar manner. 4 nodes is 14. So you have the answer. This is the 4 nodes. But here I don't think there are any large numbers. So I don't think these answers are correct. The 12 node answer we have already calculated at the top of it. Now next is the minimum height of a binary tree of n nodes is what is the minimum height that we had asked. Minimum height is also something that we had calculated. Let us go back and check what is the minimum height calculation. Where are we? Degrees, okay, skewed binary tree, and the minimum height. So the minimum height is our log base 2 n plus 1 minus 1. That's the minimum height that we had calculated. And what are the options? Let's check. Sometimes the options may not be correct. So this option is log base to n plus 1, but it is missing the minus 1, right? So if I were in this examination, of course this is the nearest, I would have actually given an answer to this, but this is a wrong answer. As you can see from the expressions that we had evaluated earlier, it has to be log base to n plus 1 minus 1, right? A binary tree has n leaf nodes. The number of nodes of degree 2 in this leaf is n minus 1. This is something we have also done. So we had said that number of nodes of degree 2 is equal to number of nodes of leaf node minus 1. This is something that we had already proved, and that's what we are trying to say here also. So that's on this particular part of the story. This says that a binary tree with the index number of a child node at 6, index number of its parent node. So from the child node, so they are saying that you have an array representation, and we have already done an array representation. So we know that the parent node is actually at I by 2 and a floor value of that, right? So what is I by 2 here? 6 by 2, which is 3. So the answer is 3, right? So that is the answer to this question. You are at index number of 6. Where is your parent? So go back and check the array part of the discussion in this lecture. You will understand that wherever we are, if that is I, so I is 6, then the parent is located at I by 2 and the floor of that, right? So that's how this is calculated as 3. So let's move on to the next problem. The next problem is saying that write a non-recursive algorithm to traverse a binary tree in its in-order traversal. Okay, so in-order traversal we have already done using the recursive algorithm, and which we have seen earlier. So if we have to do an in-order traversal for a binary tree, then the way to actually do it is use a stack, right? So what we will do is, let us take this tree, the same tree that we had used, right? A, B, C, D, E, F, right? So we'll take the same tree and whose in-order traversal we know. Let us go back and check what the answer was for that in-order traversal. Where are we? Okay, it will be here. This is pre-order, this is in-order. So the in-order traversal is D, B, E, A, C, F. That's the in-order traversal for this particular tree, D, B, E, A, C, F. So if I just keep that aside, that is D, B, E, A, C, F. So we know that the answer would be D, B, E, A, C, F. This is going to be the answer. Now let us see if we can use stack and actually create a non-recursive algorithm to answer this. So if we actually use a stack like this, and we say that when we what is in order? In order is left, root, and then right. This is in order. So we will take the same steps, and we will go left. We keep on going left till we actually don't get a null, right? So we will keep on going left till we get a null. So what is A? Does it have a left? Yes. B has a left? Yes. So if A, whenever we visit A, we will insert that A into the stack and then go left. So after A, we will go to the left of A, which is not null, so we will insert that in the stack. Then we have D, which we will insert in the stack. Then we get a null, right? So if we get a null, then we'll pop out D and we will print it, right? So D, we had gone left of D, right? So let's imagine that we had gone to the left of D here. right? And because we got a null, we popped out that. Now after this, this is printed. Therefore, now we will go to the right of D. Now the right of D is also null, so we will pop out this B also. This B also. So left and right we have taken for that node, and we got a null. Hence we popped out another element. Whenever you get null, you will pop out a stack. That's the funda. Now you go up. If you go up, then the next element that we are actually getting is E, right? Because we have we have gone to the left, then we are actually going to go to the right, right? So we'll cover all the levels right. So we will be now going top, and then we are going to the right. So in the right we see E, right? So we will push E into the stack. We'll push E into the stack. Then we'll go left and right of E. So left of E is null. Left of E is null. So if left of E is null, then take out, pop out E. So we will pop out E. Whenever you get a null, pop out. Right of E. Right of E is null. Right? So if right of E is null, pop out A. So we will pop out A. So we are done with this, and we are done with this. So now we are going to the right chain. In the right chain, we'll keep on moving left, and whatever nodes we encounter, we will keep on writing it out or pushing it into the stack, and we'll keep on moving left. So if I go to the right chain of this particular thing, the first node I encounter is C. So I'll push it into the stack. Now I'll keep on moving left. The left of C is null, right? So if the left of C is null, print C, because I'm popping out C. I'm going to pop out C, and I'm going to print C, right? And then I have to go to the right. To the right of this, then I'll keep on moving left. So at right of this I get F, right? I take F, and after that I keep on moving left, right? So the left of F is null, and the right of F is also null, right? So but the left of F is null would mean that I can pop out F. So I can pop out F now. The right of F is null, but we don't have anything to be popped out, and hence we are done with C and F. And if we go up, we are done with all the elements. All the elements are exhausted, and this is how we got the same answer as what we had done in the recursive way of doing things, right? So that's how you do the in order recursive way. The same algorithm is written on the left, so I'm not going to go through it. You can write it in your own language or write the algorithm that is there here, right? So that's on this particular problem. Construct a tree from the given postfix. All these three questions we have covered. So I just kept it to make you understand that these questions have come. So this we have done, this we have done, this also we have done, right? Go back and check in case you are unsure of it. Please rewind the video and go back there. We'll do a similar sum, so nothing to worry about. There is one more example or one more question that has come on the similar topics. Post order and in order is given. So we know that post order and in order, if we are actually doing this, then this is my root, right? So we know that this is going to be my root, right? So because we are talking about a post order, the last element is my root. So we'll write the root. Next, we will say that in order, please give me the left and right subtree. In order says that I know you have given me A, and I can only tell you that your left subtree is going to be all of this. You don't have any right subtree. So it says that you have a left subtree. I don't know what is the exact node to start with, but you will have all of this, which is E, I, C, F, J, B, G, D, K, H, L. Now what I will do, I will actually check in the post order from the right to left, which element comes first. B comes first, right? So B comes first, and B is also here. So from this list, we have B coming first in the post order. So we will write B here. With B, we will go to our friend in order and say that what is our left and right subtree of B. So it will say the left subtree is E, I, C, F, J. So it will say the left subtree of this is E, I, C, F, J. E, I, C, F, J. Okay, so EICFJ, and then it will go to the we'll keep a node for left, and it will say that the right subtree will be GDKHL. GDKHL, that is my right subtree. So let's take one at a time. So EICFJ, if I take it from the right to left, EICFJ. So what I get is IJFC. So we get C as the first element. So the C as the first element therefore becomes my root. So with C as the first element becoming my root, I will go to inorder and ask it what is my left and right subtree. So inorder will say left subtree is EI. I can see left subtree as EI, and FJ is my right subtree. And with EI, I go to the post order, and what I see is E comes first. So E comes first means E is the root. If E is the root, if I take E to the in order and say that E is, I've taken E, tell me what is the left and right. It says you don't have any left, but you have a right, which is I. And F and J, again we go to the post order, and what comes first? F comes first if we see from right to left. So then F becomes my root. I take my root to in order, and in order says that F doesn't have a left child, but it has a right. Right? So F doesn't have a left, it has a right, which is J. And then we have this right subtree to build, which is DDKHL. From the right, if I see D comes first, so D is the root, and with D, if I go here, then it says that G is going to be your left subtree, and because G is the only single node, I can put it as the root. G is going to be the left subtree, and DKHL will be your right subtree. DKHL will be your right subtree. Now DKHL, if I take it not DKHL, KHL, because D is already taken. D is already the root, right? So KHL. Now with KHL, if I go to the post order, then KHL says that H is coming first. So H is my root. With H, if I go here, then it says that K is going to be your left, and L is going to be your right. So that completes the creation of the binary tree given a post order and in order. I hope you are able to capture what we did, and this is the same thing, same way that we did earlier. Then another question which comes is, yes, this is something I had already talked about, which is the fact that given a pre-order sequence and a post-order sequence, why can you not construct a tree? Because we don't know what is the left and the right subtree, and the reason for that is pre-order gives what? Pre-order gives me the position of the root. Post-order gives me what? Position of the root. What will I do with two positions of the root? A root cannot be in two different positions, so it will always give me the same thing. Like if I say ABC and BCA, let us assume this is my pre-order and this is my post-order. Both of them are saying that A is the root, which is perfectly fine, right? So with that, I can only construct the root. Now can I say that B will be to the left and then C will be like this? Or can I say that it will be like this? It can be anything, right? So I don't know what is the left subtree of A and the right subtree of A. If I am not given in order, I don't know the left subtree and the right subtree of A and of the roots or whatever subroots, right? So hence I cannot be constructing a tree with that kind of an information. With this given and this given, I can either construct this or any other combination, but then I'm not constructing a specific tree because I don't know what is the left and right subtree. So that is the reasoning that you'll have to give. So with that, we come to the end of the initial discussions on trees and the initial discussions on binary trees, and we covered binary trees at length and also covered the traversal, which is the most important part of binary tree. I hope you had fun in understanding what we covered. I hope you have understood the way we are actually covering things from a stack perspective, utilizing the stack in order to solve the problems, both from a expression to tree conversion, that is the expression tree conversion, as well as from the non-recursive way of solving things, right? So that those are the two things which is important, and the recursive style of solving these traversals is what we have also discussed. So I hope this made sense in terms of capturing what binary tree is about. And till the time we meet next, please study hard. I'm sure your examinations are coming depending on what time you're watching this, but I hope that the videos are being useful and you can make maximum use of it. Thank you so much.